Alright, so unexpectedly I had to make a part 2 of this video, but I don't think we've lost anything. I have our stresses over here with our coefficients that we found in them already. And now I've started looking at the stresses on the boundary OA. And I've written some things down. I thought I was recording, but I wasn't. But tau xy is equal to minus 2a7x. That comes from here. But tau xy is equal to sigma x tangent theta. Okay, right there. We had written that down previously. But sigma x is equal to minus p naught y tangent p naught y. So we have minus p naught y tangent theta. And so when we go through this, we end up with y being equal to x tangent theta. So we have minus p naught x tangent squared theta, and we can solve for a7 to be p naught over 2 tangent squared theta. Now the relationship of tangent theta is equal to y over x comes from the relationship of our diagram here in our coordinate system. The tangent of this angle theta would be the opposite over the adjacent side, which would be the y distance over the x distance. Remember, our coordinate system is a little unusual that it faces this particular way. And that is also true even if we take a smaller segment here, still be y over x. So for any position x or y, the tangent of theta would be equal to y over x. Now that means that y is equal to x tangent theta, and we will use that here in just a little bit. So I guess we didn't use it in this one, but we solve for a7, the x's cancel out, the minus signs cancel out, so a7 is equal to positive p naught over 2 tangent squared theta. So now we're going to take a look at sigma y on OA. Sigma y is sigma x tangent squared theta, as we determined previously by looking at the boundary conditions and the traction vector. But we know that that's equal to the sigma y expression from our area stress function, 2a3 plus 6a6x plus 2a7y. 2a3 plus 6a6x plus 2a7, well, y is equal to x tangent theta. So now we have a little bit of work we can do to figure out the next step. Alright, so hopefully we're in good shape so far. Now, on the left-hand side, let's write it over here. Sigma x, let's write the whole line down. Sigma x tangent squared theta is equal to 2a3 plus 6a6x plus 2a7 tangent theta. Now sigma x is equal to minus p naught over y, or p naught times y. We have the 2a3, we have the plus 6a6x, and then here we have plus 2a7 was p naught over 2 times tangent squared theta. Okay, the 2's will cancel out. And then we also have a y in here. Alright, so if we bring this to the other side, we're going to have a minus 2 p naught y tangent squared theta is equal to 2a3 6a6x. Now, y is equal to x tangent theta. So that's minus 2 p naught x tangent cubed theta is equal to 2a3 plus 6a6x. Equating coefficients tells me that a3 has to be equal to 0. And if I solve for a6, the x's cancel out, equating coefficients on similar terms, then that would give me a minus 1/3 p naught tangent cubed theta. All right, so with that, I think we found all of our coefficients. So a3 is equal to 0, and a6 is equal to minus 1/3 p naught tangent cubed theta. All right, so that is a fair bit of work. Let's write down the area stress function that results from all of that. All right, so there's what we wrote down for our Aries stress function form. And based on what we have here, we know, let's do a different color. The terms that do not show up in the stresses really don't matter what they are in our area stress function. So for example, we don't need to worry about the A naught. So, or A1, or even A2. So the first one we get is A3, which is 0. A4 is equal to 0. A5 is equal to 0. A6 is equal to minus 1/3 p naught tangent cubed theta. Then we have an x cubed. A7 is equal to p naught over 2 tangent squared theta. Then we have an x squared y. A8 is equal to 0. And A9 would be minus p naught over 6. Then we'd have a y cubed. Where did A6 go? There it is. Okay. So I think I have all of my terms. So we have 6, 7, and 9, an x cubed, an x squared y, and a y cubed. So this ought to be our Aries stress function. So that should answer our part B, and then explain your choice. Well, we did all the work and we talked our way through it, so that should be covered. The next part here says, let the body force of the dam be rho g in the y direction, where rho is mass density and g is gravity acceleration. Include the effect of body forces determined explicitly in terms of known quantities, the complete expressions for sigma x, sigma y, and tau xy. It says, hint, note that the body force rho g is derivable from potential function minus rho g y. All right, so what I'm going to refer you to then is in our book, equation 5-4.9, which tells us how to find the stresses given a potential function for body forces. Okay, so here's the information for the body forces and so forth. So I'm going to copy that over into my slide here. Let's make a little bit of room. Alright, so let's start with taking our partial derivatives of what we have here. So let's go with partial derivative of f with respect to x. Okay, I'm going to have minus p naught tangent cubed x squared plus p naught tangent squared xy. Second partial derivative with respect to x. going to be a minus 2 p naught tangent squared theta x, and then a plus p naught tangent squared theta times y. Okay, and so that would be our sigma y. Second partial derivative with respect to x and y. Okay, so now take a partial derivative with respect to y. This term goes away, and this term will be p naught tangent squared theta times x. Okay, now that would be minus tau xy. And then we need the partial derivative of f with respect to y, and that would be a p naught over 2 tangent squared theta x squared minus 1/2 p naught y squared. And then finally the second partial derivative of f with respect to y twice, zero contribution here, and then we have a minus p naught y, which would be sigma x. Okay, so these are the stresses without accounting for the body force terms. Okay, so note that the body force rho g is derivable from the potential function minus rho g y. So let's see, determine explicitly in terms of known quantities the complete expressions for these things. All right, so let's take a look at our equilibrium equations. We know it's a partial derivative of sigma x with respect to x plus the partial derivative of tau xy with respect to y equal to 0. No matter what we do to this term, partial derivative of that is 0, and partial derivative of tau xy with respect to y is 0, so we're okay there. So the next thing we'll look at is we're going to take a look at the partial derivative of tau xy with respect to x, and then we're going to look at the partial derivative of sigma y minus v when I showed you that section in the body forces with a potential function. So we have that. Now the partial derivative of tau xy with respect to x is going to be p naught tangent squared theta, and then we're going to have this term here. That'll be the partial derivative of sigma x minus v with respect to y, and we need to ensure that that is equal to 0. And in fact, it's actually a minus sign right here because this is negative. All right, so what I'm going to do at this point, we have ourselves a differential equation. I'm going to separate these out, so I'm going to have the partial derivative of this quantity, sigma y minus v, partial of that with respect to y is equal to plus p naught tangent squared theta. I'm going to integrate both sides with respect to y. That'll leave me with sigma y minus v over on the left-hand side. Over on the right-hand side, I have p naught tangent squared theta times y, and I could have an arbitrary function of x. And I think if we really got down to it, at most it would be first order in x. So maybe some constant times x that we have in there. All right, just enough room to write down the next line. They told us what v is. All right, so we're going to have sigma y is equal to v plus p naught tangent squared theta times y plus ax, but v is equal to minus rho gy. I'm going to have a P naught tangent squared theta minus rho g times y plus an ax. Alright, now we have a little bit more work to do to find ax. I know this is a long problem. I understand that. Hang in there. Let me get a little room here. Alright, so we have an expression for sigma y, but we also know that from over here, let's see, in terms of the shearing stress, sigma y is equal to tau xy tangent theta. Alright, let's see what we can do with that. Did we have an expression for tau xy? I believe we did. I believe we had tau xy is equal to minus p naught tangent squared theta times x. So minus p naught tangent squared theta times x times tangent theta is equal to the stuff times y plus ax let's see. We have our relationship for y, so I guess we're going to need to put this stuff in here. P naught tangent squared theta minus rho g times y and y is equal to x tangent theta. Alright, then we're going to have a plus ax. Alright, over on the left hand side it looks like we have a minus p naught tangent cubed theta times x. The x's look like they'll all go away, and maybe fingers crossed. Let's see here. We got a minus p naught tangent cubed theta, and here this is actually a tangent cubed theta. We're bringing it to the other side, so that'd be a minus 2 p naught tangent cubed theta plus a rho g tangent theta. Alright, so now that we know what A is, we can put that back in here, and then I think we're finally done. Alright. Very long problem, but it kind of ties all the things together that we've been talking about with respect to Airy's stress functions. And once you have that stress function, then you have the stress fields, the strain fields, and so forth. Again, I want to give you a little appreciation for what it takes to build an Airy's stress function. Not at all an easy problem, but with some guidance on the polynomials, then it's possible. So again, I understand it's a long one. All right, hang in there, and that'll do it for this particular problem.